I would request all the participants to mute your mics.
Subhash, you can start right now. Okay.
Yes, sir. A warm welcome and good afternoon to one and all present here. I'm Subhash R, IEEE RAS Student Brand Vice Chair from Department of Electronics and Communication Engineering. On behalf of St. Joseph's Institute of Technology, I'm here to volunteer for today's session. Now, I would request Dr. Jnana Kausalya Ma'am, Professor and Head of Staff and Student Affairs to take over and address the session.
Good day, Mr. John D. McDonald and dear participant. This is Dr. C. Jnana Kausalya from Department of ECE, St. Joseph's Institute of Technology, St. Joseph's Group of Institution, India. On behalf of St. Joseph's Management and IEEE Organizing Committee, I'm very happy to welcome today's speaker, Industry Guru, Mr. John D. McDonald, Smart Grid Business Development Leader for GE's Grid Solution Business USA for the second day of 7th webinar series. Our gathering, it takes on a special meaning and moves to the next level due to Mr. John's presence. Welcome, Mr. John. And it is our honor to mention our sincere gratitude to our chairman, sir, Dr. B. Babu Manoharan, Managing Director, Madam, Mrs. Jessie Priya, Director, sir, Mr. Sashi Shekhar, and Principal, sir, Dr. P. Ravichandran, for their great support to conduct this event. We have with us participants from different organizations, and we are grateful to all the participants and welcome you all the participants. Welcome, Mr. John. Thank you. Now the session is over to Mr. Shubhas to introduce our today's speaker, Mr. John McDonald.
Thank you, ma'am. Thank you. I would like to share a few words about the speaker. John D. McDonald is a smart grid business developer leader for GE Grid Solution business with 45 years of experience in electronic utility industry. He received his Masters of Engineer and Bachelor's of Engineer degree from Purdue University and MBA degree from University of California. John is a life fellow of IEEE member for 48 years and CAGERE member for 13 years. He is a past president of IEEES and past chair of IEEES Substantial Committee and IEEE Division past director. John currently has a VS technical activity from US National Committee of CAGRE, and John has published over hundreds of papers, articles, and co-author for 5 books. And he has a US patent too. We are glad to have you, sir, in the series of SAVANT organized by St. Joseph's Institution. Before we start the series, I would like to tell few instructions to be followed by the participants. Kindly post your queries and questions in the chat box at the end of the session. The attendance link will be posted at the end of the webinar. Now, I invite our speaker of the day kindly start the session. Yes, sir. Yes, Kathleen is yes.
Thank you. Thank you very much.
Thank you, sir.
Happy to participate. I really appreciate the invitation to be part of your program. This is a topic that I've spent a lot of time with for many, many years, both in consulting, doing international consulting before I joined GE, and since I've joined GE over 12 years. So it's big data, the concept of big data, IoT, Internet of Things, enterprise data management. And then I've focused for the last couple of years on the new data requirements of drones, or sometimes we call them unassisted aerial vehicles, UAVs, and robotic inspection devices. As Subhash just said, I actually have 46 years of full-time work experience. I've written about a little over 150 papers and articles, 5 books, and I have 1 US patent. I'm very, very proud, though, to say that I've been an active IEEE member for 49 years. Next year will be my 50th year. And I've been very active in the IEEE Power and Energy Society, which today is the second largest society of the 39 societies in IEEE. So I've led standards work in IEEE for 35 years and done a lot of international work. So all of this experience will be part of my program today. And my email address up there by my name, johnd.mcdonald@ge.com. I'm going to reference several articles I've written, some books during the talk. And if you want copies of any of the articles or information on the books, just send me an email. Please send me an email. The one book, the most recent book, I wrote the first chapter of this book, was published in 2018, called Big Data Application in Power Systems, okay? And the first chapter I wrote is titled A Holistic Approach to Becoming a Data-Driven Utility, okay? It's the first chapter in the book. So again, if you want any information on articles or books, just send me an email. So these are the topics that I'll be talking about. We'll start with key industry societal trends. Then what's very important is types of data. The foundation is the data. So let's look at the data first. Next would be how do we use the data? So we'll talk about the Internet of Things and new software analytics. Then what's extremely important for success in any organization is the convergence, or the bringing together of the information technology and the operations technology groups within the organization. We call it IT, OT. We'll talk about industry standards. You know, with the IEEE and the different societies in IEEE, standards are extremely important. And the two key words today are integration and interoperability, okay? When we put a solution together for customers, it's typically technology components from different suppliers, different vendors. But these components have to be able to communicate with each other, and they have to be able to exchange information with each other successfully, communicate and exchange information. And the only way they're going to do that is if they comply with the same set of standards, okay? Of all the 39 societies in IEEE, the IEEE Power and Energy Society writes over 50% of all IEEE standards. So that's why, you know, we in the IEEE Power and Energy Society, we have 17 technical committees and 3 coordinating committees. And I chaired the substations committee, writing all the standards on substations. And one of my specialties is automation of substations. So this is, I want to talk about standards. For 5 years, I chaired the board of all the smart grid standards work in the United States. And then what's really exciting is the new sources of data with the unmanned aerial vehicles and robotics. And we'll talk about that. So let's look at trends. As I said, we're transitioning from devices and systems to holistic solutions. A device is a microprocessor-based device, right, with two-way communications. It was in the 1980s that we first saw in the industry the very first microprocessor-based devices. The difference with these in the 1980s was they had two-way communications, okay? And so these devices had two-way communications. And I was chairing standards work in the substations committee in the 1980s. And we developed the term intelligent electronic. That's now an IEEE standard term. But we came up with that in the 1980s. We needed a term to characterize microprocessor-based devices. Okay, the biggest difference with these, though, is that they have two-way communications. So they aren't standalone, be a node in a network, okay? And that's what we mean with a solution, okay? The integration of these together to form a holistic, which means company-wide or enterprise solution for the customer. So we want to transition, we're transitioning from devices and systems. I'll show you examples of systems to a holistic solution. The reason we're doing that is solutions have greater value to the customer than a component itself, okay? And why this is important is we're teaching students at universities to see the big picture, okay? Be happy with the relay or the component, but try to use that component as a node in a network with other components and see the big picture, okay? In fact, at Georgia Tech here in Atlanta, we teach systems engineering, you know, teach students see the whole, look for the big picture. Success is technology, standards, and policy, three. But standards, again, for interoperability and integration, and policy, you know, the policy makers in the country, they set the policy, and hopefully policy is the greatest incentive for a customer to spend technology to spend money on your technology, to buy it, okay? It's the greatest incentive. So we spend a lot of time with policymakers to influence them so that the policy supports customers to spend money to buy our technology. Now, the easiest thing for an engineer to do is develop the technology. The most difficult thing is to change the culture of the customer. Okay, that's what I mean here, culture. You have to convince the customer to do something new, to use your new technology. And two parts of this is closed loop control. Having confidence in the logic out in the field to take the human out of the loop and close the loop. Let the logic do its thing without a human. A human slows things down, okay? I want a grid that is resilient and is self-healing. It can heal itself. When a problem occurs, it detects it, it locates it, it isolates it, and restores service upstream and downstream of the faulted segment automatically, like within a minute, okay? But I have to be able to close the loop on the logic. And then we've distributed the intelligence from only being in the control center to now being down in the field, okay? So we have a hierarchical architecture of different levels. One is at the control center, one is at the substation, and one is at the edge of the grid, okay? We're putting low voltage power electronics at the edge of the grid. We call these low voltage network dynamic grid edge controllers, okay? Grid resiliency, we want the grid to be more resilient, which means the electric grid, when it's stressed by something like an extreme weather event, okay? The measure of its resiliency is how well it withstands the stress, okay? So we design redundancy, reliability with the equipment, with the architecture, and then when it's stressed, we see how resilient it is. One of the things that we've added to the grid is microgrids. A microgrid is a small grid unto itself that if there's a problem on the big grid, we can island or isolate the microgrid and it can operate on its own. Typically, microgrids have distributed generation, which is solar and wind, which helps it operate on its own or islanded, okay? We'll talk about big data. The automation platforms today have cloud components, so we're using the cloud. And we're also using more social media. You know, we're convincing customers using the call to tweet, right? Use social media, send a tweet, use Twitter and send a tweet. If the electricity goes out at your home, instead of trying to call the utility, which is difficult, right? Because you have no electricity, you have to use your smartphone and hopefully the battery is charged. You know, use Twitter. I can send a tweet to my electric utility and say, hey, electricity, you know. So we're using more social media. One thing that's extremely important, as I mentioned, was the convergence of the information technology part of the organization and the operations technology. Operations has a lot of very valuable data. We need to take that data across the firewalls of the operations system, you know, operations is very cyber secure. So we need to go across the firewalls and over side of the utility, which is the IT side. Now, when utilities today add distribution, sun, wind, photovoltaic panels, it makes their distribution part of their grid very complex, because now electricity can flow in two directions, not just from the source, but from the distributed generation stream. So they're putting in what we call an ADMS, an Advanced Distribution Management System. This is a computer-based control system in their control center that manages the complexity of the distribution system and also optimizes its operation. Well, 30% of the cost is the cost from the supplier, from the vendor, but 70% of the cost is the integration of that system with other systems in the utility, okay? So that's why I keep on integration and interoperability, two key words today. And then a very important saying today is that before we think about a smart grid, we need to have a strong grid, okay? Strong grid before smart grid. By smart grid, we mean adding new things to the grid, right? And adding new technologies. But you don't want to add anything new on top of that may be weak or have some weak areas. We need to have a strong grid. And there's two parts to a strong grid: communications infrastructure and the IT, or information technology infrastructure. Communications is the enabling technology that allows us to automate, right? Without communications, we wouldn't be able to automate. We wouldn't be able to optimize the operation. Communications is foundational. It's the foundation. Without a IT infrastructure that has connections across the entire utility, we wouldn't be able to do enterprise data management, right? We wouldn't be able to send data from the operations side to the IT side, to the corporate network. So the IT infrastructure must be connected, must not have any, okay? So these two are very important. That's part of the strong grid. You know, make sure you have a strong grid before you add anything new. So to really get the full benefits of our investment in data sources, we need to make sure that we're managing the different types of data in the data sources. Now, I did many projects for many years, and I realized that after the 1980s, when we first saw the microprocessor-based devices, or the intelligent electronic devices, IEDs, we weren't managing the different types of data, okay? So I wrote an article in 2003 in IEEE Power and Energy magazine. This is the magazine for the Power and Energy Society. And I introduced some new concepts to the industry called operational data and non-operational data. Today, these are industry standards, okay? The operational data is that we're very familiar with. This is the information in the field that we need to send to the control center, that the operators in the control center use to monitor and control the grid, okay? And this data is coming in every 2 seconds, all the time. It's a time series of data, a sample of the voltage, of the current, of the real power flow in megawatts, the reactive power flow in megavars, okay? Very, very important information, such as the open and closed status of a circuit breaker or a switch, the current in amps, the voltage around the system, the loading on the transformer, both real and reactive power, and alarms, alarm information, okay? Important information, and this is what we're used to. But the new microprocessor-based devices gave us a new type of data that we weren't used to, and we didn't know what to do with it. And I call this non-operational data, because the primary user is someone other than the system operator. And in the projects I've done, there could be 25 to 30 different groups in the utility organization that have a need for this data. Examples are engineering, maintenance, asset management, okay? Now, what's important is, I'll go back, operational data is always points of information, okay? Voltage, current. It could be a status point, a digital point, or it could be an analog point, but it's points. Non-operational data is different. It could be points, or it could be a data file, okay? And by a data file, I mean it could be a digitized waveform from a microprocessor-based device, right? Like an oscilloscope, a waveform that we've digitized, okay? It could be a point, which is the circuit breaker contact wear, which we would want to send maintenance, right? Or in a transformer, it could be how involved gas is in the oil of the main tank of the transformer. Again, maintenance would be interested in that. So non-operational data is points or files, okay? Now, if we compare these two, operational data is, we said, individual time sequence points, where non-operational could be points or it could be a data file. Operational data is typically real-time or near real-time, where non-operational data is typically historical trends, okay? And operational data, we typically communicate that with what we call standard communication protocols, non-proprietary, where a data file and non-operational data, we may need a vendor-specific proprietary ASCII protocol to extract it, okay? So there's some differences, but the equipment today, the technology today can support these. Let's look at the Internet of Things. Sometimes you see this in industry called IIoT, which means Industrial Internet of Things. Same thing. And new software analytics. Why are analytics important? Well, when we have data, how do we convert the data to information? The data itself is raw. It doesn't have value. We need to convert it into information. Information has value. And we do this through different software analytics, okay? So Internet of Things is really what we call the next productivity revolution. So the question is, how can we leverage this? How can we take it to value to our organizations? Well, first of all, what is the Internet of Things? So we're connecting intelligent machines, okay, with big data and analytics, and with people at work, okay? What's interesting is we're connecting people anyway, any place, and any time for intelligent operation, okay? That's because you, in the near future here, you won't have to go get the data that you need. It'll be readily available. It may be in your Google glasses, okay? You're wearing Google glasses, and you just look in your glasses and you'll see the data that you need, okay? But it'll be readily available, okay? In other words, there'll be greater connectivity. So this is intelligent machines with big data and analytics and connecting it with people at work, okay? Tremendous savings if we take advantage of this. Now, then the question is, how do we use this data? How do we convert it to information? Well, we look at different areas where we can develop new analytics. In other words, where can we provide new value to the customer? One is in smart metering, right? The meters today that measure electricity use are microprocessor based with two-way communications. They have a lot more capability than the older electromechanical meters. Second would be outage, outage insight into the outage. Third would be reliability of the grid. Fourth would be renewables, the distributed generation, the photovoltaic panels, the windmills, the wind turbine generators that we're adding. And the last is the end use customer, okay? When we add technology to the customer's home, we need to engage with the customer. We need to explain to the customer what the new technology is and what additional benefits the customer will receive with the new technology. For instance, with a smart meter on my home here in Atlanta, Georgia, in the United States, I can go to a website provided by the utility and I can see my energy usage, right? Very detailed plot of my energy usage, and I can compare that with other homes that are the same size as my home, with my neighbors, with other people in my city. I can also I've given the utility characteristics of my home, the type of home it is, the type of appliances I have, and they can tell me if I'm doing a good job of conserving energy, okay? This is all much more value that can be provided to the end use customer. So we need to converge. We need to bring together information technology and operations technology, and that helps us then manage data across the enterprise, which means across the whole organization. So if we can integrate the electrical and information infrastructures with automation and information technology, it gives us comprehensive solutions, okay? We will improve the reliability, the operational performance, and the overall productivity of both the grid and the workforce. We will deliver increases in energy efficiencies and decrease in carbon emissions. So a couple of the advantages with what we're doing with Smart Grid is we help the environment and we help society, okay? Help the environment and help society. We will deliver increases in energy efficiencies. We also empower customers to manage their own energy use and save money without compromising their lifestyle. So we're giving the customers technology and tools and support so they can manage their own energy use in their home and save money, but without compromising their lifestyle. If they're going to have a party at their home or have a lot of people, a lot of family over, and it's a very, very hot day, we want them to be able to use their air conditioning so that they have a comfortable home for all their family, right? We don't want to have them have to have a very hot home to save energy because of the technology. You want people to enjoy their life, but at the same time, save as much money as they can, okay? And then we want to optimize the renewable energy integration. How can we optimize the integration of photovoltaics for using the sun and wind turbine generators with what we call wind farms, right? A collection of wind turbines, and enable broader penetration. So the one big advantage of Smart Grid is there's much more focus on the distribution part of the grid, right? The part of the electric grid that brings the electricity to the customer, the distribution part. So information is extremely important, right? Converting data to information, making sure we have the right data, we're extracting the right data in our organization. So on the left side is the typical situation today with many organizations. And what we say is that each group in the organization has its own systems, okay, and obviously each of these systems has a lot of data. They have their own microprocessor-based devices. Remember, we call these intelligent electronic devices, or IEDs, and they have their own databases and data repositories, collections of data. Problem today is that each group works by itself. We say they're very siloed, There's a silo around each group. They're incentivized by their organization to do well only as their own group, not to share information with others. And this is a real problem because the organizations are not getting the full value from their investment in the data sources. The goal then, and what I've been doing for many years with organizations, is to help them break down the silos and become holistic, right? Become seamless. Break down the silos and have all the groups with each other, okay? It shows a federated data mart, IT architecture, infrastructure within the organization that brings together all the operational systems, all the microprocessor-based devices, and all the data repositories so everyone can share information. This is extremely important and necessary for enterprise data management. Okay, the benefits of this are that what I'm showing here is just a standard hardware and firmware architecture in the substation of the electric grid. We have intelligent electronic devices here that are collecting information from different parts of the grid. They're communicating upstream to what we call a slave data concentrator. Think of this as kind of like a gateway, a data concentrator. It's collecting all this information and concentrating it, and then it sends the information upstream to a master data concentrator in the substation. The master data concentrator then sends that information up to the enterprise. The operational data will go to the control center here. And these are three different types of systems in the control center. The energy management system, or EMS, is what controls the generation and transmission parts of the grid. The distribution management system controls the distribution part of the grid, and the outage management system keeps track of which customers are without electricity. Then the non-operational data will go to this federated data mart, this repository here on the corporate network. So this is on the IT side of the electric utility organization. This is the operation side, and this is the IT infrastructure, okay? The goal then is that all the data sources in the utility, all the light blue data sources here, have provided all the information that's needed by all the different business groups in the utility. These are all in green, okay? So all the users in the utility have the information they need to provide the greatest value to their organization, okay? Now we can do this steps, okay? First, I would hold a workshop within the organization to bring all the stakeholders, all the different groups together and teach them and give them the same level of understanding in enterprise data management. We would then review the data maps of all the devices, systems, and repositories. This means what data is available. And let's determine and identify which of these data points and files have the most value to somebody in the organization. And we would create standard data template. In other words, when we're using this device, these are the data points and files in that device that we want to extract because they have the most value. Then we would develop an enterprise data requirements matrix, which maps the data points of value to the different stakeholder groups that'll use the data. And then we would review the substation automation architectures. We just saw a standard architecture with data concentrators, both slave and master, because we want to extract the points of value, concentrate those points, and send them across the firewall to the enterprise data mart on the corporate network. Now, I've applied these concepts with many, many different organizations, and I've written a lot of articles, which I call case studies. And if you're interested in any of these articles, let me know and I can send you copies of them. Now, industry standards, I said, are extremely important. In 2010, I was elected to a board called the Smart Grid Interoperability Panel for the United States, SGIP. And I call it Smart Grid Interoperability Panel. This was a group the United States put together to coordinate all the smart grid standards for the United States. I was one of 25 experts elected to that board, and then the board elected me to chair the board. So from 2010 through 2015, I chaired this board. We managed and coordinated all the smart grid standards work for the United States. We put together the smart grid conceptual reference model at a high level. How do we draw, what is smart grid? Okay, and we said it's 7 domains, and this is the way this is what the 7 domains are. You know, the generation, the transmission, the distribution, and the customer. So this is the electric grid, right? We generate, then we need to transmit it to where the customers are. Then we need to lower the voltage with the distribution system, so it's at a lower voltage at which the customers would use the electricity, and then the customers themselves. Then we have markets, we have operations, and we have the service providers. Okay, so this is called the Smart Grid Conceptual Reference Model. It's an industry standard. But the biggest challenge for us was the different standards development organizations in the world. Okay, these are called SDOs. These are the organizations that write the standards that govern what we do. Okay, and IEEE initially said we have over 100 standards involved with smart grid. Okay, another standards development organization is the IEC, called the International Electrotechnical Commission. They're based in Switzerland. Very, very important group. They have over 100 standards involved with smart grid. So how is the industry going to determine what standards to use? Let's say I have a product, I'm developing a product, or let's say I'm at an electric utility and I'm developing a substation automation system. How do I know what standards I should include, right? I can't go, I don't have the expertise and I don't have the time to go through hundreds of standards. This is very complex. So what we did was we went through these standards and we determined that there were 16 standards that were the most important for what we call smart grid. We call these the Smart Grid Interoperability Standards. I call them the foundational standards for smart grid. And we did this to help the industry. We said, if you just focus on these 16 standards, it will cover every aspect of the grid, from generation, transmission, distribution, customer, cybersecurity, customer automation in their homes, everything, okay? And these are the foundational standards. So this was tremendous help to the industry, tremendous help. And we spent a lot of time doing this, publishing this to help the industry, okay? What really makes it easy today is that if I look at 3 different levels of the grid, let's say I look at control center to control center. This is where electric utilities are exchanging information with each other. This could be country to country, or within a country, this could be one large utility with another one. There's one industry standard that everybody uses for this communications, and it's called the Inter-Control Center Communications Protocol, or ICCP. One global standard. From the control center to the field equipment, there's really 2 standards that we use, and it depends on where the supplier is located. If the supplier is in North America, which is the United States or Canada or Mexico, we would use what's called Distributed Network Protocol 3, DNP3, which we took through the IEEE standards process, and it's IEEE 1815, okay? Or if it's a European supplier, they standardize on what we call IEC 870-5. 101 is for serial communications, 4 is for network communications, okay? And then if we're down in the field, if it's a North American supplier, we would still use DNP3 or IEEE 1815, but truthfully, you know, the global worldwide standard for substation automation and for field communications is IEC 61850. Okay, that's the worldwide standard. So the beauty of this is we've gone from many different choices, many different, to converge on just a few. Okay, so the board that I chaired for 5 years on coordinating all the smart grid standards, we had two goals. One was to coordinate the standards, but the second goal was harmonize the standards that the US was coordinating with the rest of the world, right? We don't want every country to have its own standards because this prohibits trade, right? If I develop something in the United States and I'm trying to sell it to India, you have your own set of standards and US has its own set of standards. You will look at technology and not understand how it operates because it's developed based on my set of standards in the US and you have your own set of standards. So to help facilitate, right, to help encourage trade, we want to harmonize standards globally. We want everyone to use the same set of standards. This really helps countries to each other, okay? And we spent a lot of time, I spent a lot of time with other countries working with the other countries, okay? We did. So what's exciting here is these newer sources of data, unmanned aerial vehicles and robotic inspection devices. So this photo here is a robotic inspection device on a high voltage transmission line in Canada, in Quebec, Canada. The utility here is Hydro-Quebec. So let's say the data that we get from these sources can be photography, it can be imagery, which is we call LiDAR and FODAR. These are images that come from, say, the drone, okay? Or it could be infrared sensors where we're detecting hotspots, right? Infrared. We use this data to inform, and this is why this is so important, because this data has tremendous value to the electric utility. We use this data in asset management programs, right? What is the health of the asset? Okay, we can tell from some of this data. We use it in geographic information systems. A geographic system has the digitized maps of the entire service territory of the utility and a facilities database of every asset that utility owns. All the wood poles, all the conductors, all the equipment in the substations is all in a database with geographical coordinates, right? Geospatial coordinates. Third is the outage management system. We use the information outage management. And the fourth is storm damage assessments. Okay, so this data, and this is just a small number of the uses of this data, okay? Now, how do we analyze the data? So we're getting these images from the field. We want to pursue automated image analysis to create value. We want to automate the analysis of the images. Today, some organizations have humans watching of streaming video, and that's really not practical or beneficial. It's not a good use of resources. Okay, we need to automate that process. So, you know, look at the images and know what to look for in the image. We may look for corrosion on a connector. We may look for a break in conductors. Okay, but we need to automate that process. So I conducted a brief ad hoc survey, which included utilities, consultants, and power industry groups or consortia. And it really showed me how a coordinated industry response to the emergence of these unassisted aerial vehicles and robotics can really speed the time to value, okay? So some of my observations were that the power utility use of these data sources is really in its beginning, its infancy, just starting. But these are both an effective and efficient means to monitor the infrastructure health and perform remedial work. So they have a lot of value. So how the raw and analyzed data is stored, routed, or otherwise made available across the utility organization, it's different for each utility. In other words, there's no standards today. There's no consistent use of this information, okay? So my recommendations are de-silo. In other words, break down the barriers between the groups, de-silo the utility and its approach to data management, because we want to achieve organization-wide value creation. It creates a positive business case for new technologies and makes the power utility more nimble and competitive. By being more nimble, we mean it can make decisions faster, okay? And I'm saying because it's just starting, it's in its infancy, now is a time to apply holistic data management thinking. Holistic data management thinking means let's think across the whole organization and how we can use the unassisted aerial vehicles and robotics outputs to create value. The power industry, we should determine and pursue common requirements for these data sources, for the technologies, and push their use, okay? But we also want to push that the purveyors, in other words, the companies that develop these should comply with industry standards. So we need to adopt standard data formats and data analytics based on open source architectures and true enterprise-wide integration of the information. We want to avoid proprietary solutions that limit the utility's future options. You should never get yourself into a proprietary solution. You're captive. You have to use one vendor who's developed this approach. You don't have the choice of going out to industry and having a competitive bid and using industry standards to be able to get technology from different vendors. You're stuck with the same vendor, okay? So I want to finish here, and we should have time for questions. I want to finish and emphasize that there's a no-cost free webinar available to all of you from the IEEE Power and Energy Society. I put this together a couple of years ago and I've updated it. I give this often because it's in demand, particularly from students and young professionals. It's called Key Insights to Career Management, okay? And I reviewed my 46-year career and 49 years as an IEEE member. And there were 12 key decisions I made in my career that influenced the rest of my career. And by knowing these 12 key decisions and having this information early in your career, you can do a really good job of optimizing your career choices, okay? So again, you can go to the IEEE Power and Energy Society Resource Center and you can on the name, which is Key Insights to Career Management, or my name, right, John McDonald, and participate. Watch this webinar. It's only 1 hour. You can hear what I have to say. You can see me talking, and you can see my PowerPoint material. Okay, so I say the talk is designed to manage your career. There's 12 important things to keep in mind when living and managing your career to achieve your goals. And I explain and explore these with examples. I use a lot of photographs from my family, from IEEE, from Seagray, from business trips, and 46 years as an engineer, manager, and executive managing people's careers, and 49 years as an IEEE member. I'm an IEEE Life Fellow, and 14 years as a Seagray member, and I'm a Seagray Distinguished member. So remember, your career is your career, and understanding your priorities, which can change, and your company's objectives, you really want to optimize these and have a rewarding and fulfilling career. So that's only 1 hour of your time, and you know, many young people will watch this, apply it, and then watch it again, because you can learn something every time you watch it, okay? And I'll finish with that. Just wanted to let you know that that's available to you. Thank you for the opportunity, and if there's any questions here, I'd be happy to answer the questions.
Yes, sir. Yes, sir. Thank you, sir. And we have a few questions, sir. Uh, what is ADMS?
So that's called Advanced Distribution Management System. And as I mentioned, as we integrate renewables onto the distribution part of the grid, we design the distribution part of the grid for electricity to flow in one direction only, from source to load. When we integrate distributed generation, we now have electricity flowing in two directions, because we have a load side contribution now. This makes the distribution part of the grid much more complex. So an ADMS is an Advanced Distribution Management System. It's a computer-based control system with very advanced software that manages the complexity of the distribution part of the grid and optimizes its operation.
Yes, sir. Thank you.
Let me add, if anyone is interested in it, I co-wrote a book with a professor from with Professor Minnie Thomas. She's from Kerala. She's a professor in Delhi at Jamia Millia Islamia University. Right now, she has a 5-year assignment from the Indian government. She's the NIT director in Trichy, okay, Professor Minnie Thomas. Minnie and I spent 2 years and wrote a book called Power Systems SCADA and Smart Grids. SCADA means Supervisor Control and Data Acquisition. A SCADA system is an energy management system for generation transmission part of the grid, an ADMS for the distribution part of the grid. So in this book, there's 335 pages in the book, and we talk about these systems, okay? So this book was published in 2015, Power Systems SCADA, and again, it's a good source of information if you want to learn more about an ADMS.
Yes, sir. Thank you, sir. It was more informative. And we have one more question. Why should we need operational data?
Well, you have to know, I mean, if you want to make sure that the electric grid is stable, doesn't have any outages, is economic, right? Is operating the way it should, you need to know what's happening out in the field, right? You need to know what, you know, is the operation, right? Are we okay? So the operational tells us how the grid is operating. And that's why we want this data we want it frequently. We want it every 2 seconds. So we typically get this data every 2 to 4 seconds. And it's, you know, hundreds of thousands of pieces of information coming to the control center to let us know, because if any of these data points exceed a limit, we get an alarm, and that alarm tells us there's a problem, okay? And we need to address that problem right away before, because if there's a problem and we don't address it right away, the problem could get worse. And we don't want a blackout, right? Because if this problem gets worse, in other words, it cascades, it could cause the whole grid to go down, which means we have a blackout. That would be the worst situation. So that's the operational data gives us on a time series basis, frequently tells us what's happening with the grid. We need to know that.
Yes, sir. And we have one more question. Is MQTT sufficient to provide security in IoT-based application? Is sufficient. MQTT.
Sufficient? Yeah.
To provide security. Yes, sir.
That's part of it, but it's not totally sufficient. Okay, when we develop new technology today, we incorporate cybersecurity into every step of the life cycle of developing that product. Cybersecurity is extremely important. We look at I have a separate presentation just on cybersecurity in terms of what we're doing today, you know, to make sure that the grid is secure. we look for vulnerabilities in the grid. We try to penetrate the grid in different places to see if there's vulnerabilities. We do everything we can for protection. In this presentation, I show examples of where equipment was hacked, examples of where the grid has been hacked, and how the hackers were able to to penetrate the grid, and what we've learned from that and how we can prevent it. So MQTT is one part of it, but it's not everything. There's a lot of aspects. We have to look at different threats, right? We have to look at different ways that we can address the vulnerabilities, and so we spend a lot of time. Two parts. One is cybersecurity, and the other part is privacy of information, right? We want to make sure that, for instance, the information from your smart meter on your electricity usage is not given by the utility to anybody else or sold to anybody else, that it's private and it's your information.
Yes, sir. And we have one more few questions, a couple of questions. How do I use the data generated from IIoT?
Well, one thing that we do is we first identify what data we need, right? And it's in different data sources. Then with IoT, what we do is we connect all these data sources together. So one aspect of the future is much greater connectivity. So we take the intelligent machines with big data and analytics and with people, and we connect all these together, okay? And then there's many ways to use this data. I'll give you some examples. We're using this data today called storm preparation. So instead of waiting until a storm and we see the damage from the storm, and then we try to restore electricity, we want to be proactive, not reactive. So what we've done is we've moved the industry from being reactive, wait till it fails, to be proactive. I want to eliminate the failure or minimize, right, the impact of the failure. So I look at different health information and I predict a problem before it occurs. So in one way we use the data is we call storm preparedness. We look at a storm that's coming, we forecast what damage that storm is going to do, where it's going to do the damage on the grid, what equipment may be damaged, what people we will need, what experts we will need to replace the equipment. And we actually put replacement equipment at that part of the grid before the storm occurs, and the experts that are needed the equipment, we move them out, right, to where they're needed. This is all happens before the storm occurs. Okay, we're preparing for the storm. We're using the data, using intelligence, we're using machine learning, we're using artificial intelligence, and we're applying that with data scientists today to develop these new analytics. So there's many new analytics that we're developing. They provide tremendous new value to the industry.
Thank you, sir. Thank you, sir. That's the end of question and answer session. Now, thank you, sir, for your stimulating and fantabulous session. And I invite Dr. Rohini Ma'am, a professor and head of lab affairs, to express her gratitude.
Good morning, sir. John, sir, good morning.
Great. Hi, Rohini.
Good evening, all. Myself, Rohini, Dr. G. Rohini, professor. It's my privilege to have been asked to propose a vote of thanks on this occasion on behalf of Department of ECE, St. Joseph Institute of Technology, St. Joseph Group of Institutions. IoT and drones will be most impactful than we think, as nowadays people recognize in positive ways to help society. I feel proud and honored to spell the word of thanks to our guest speaker, Mr. John D. McDonald, Smart Grid Business Development, leader for GE's Grid Solution Business USA, for his inspiring speech on requirements of drones and robotic inspection devices. My heartfelt thanks to our beloved Chairman Sir, Dr. B. Babu Manavaran, for his consistent in conduction of this program. My sincere thanks to our Managing Director, Ma'am, Mrs. Jessie Priya, and our Director, Sir, Mr. B. Sashi Shekhar, for their guidance in conduction of the program. I would like to express my deep sense of gratitude to our Principal, Sir, Dr. P. Ravichandran, for his support to his conduction of this program. I also thank our Head of the Department and IEEE Chapter Advisor, Dr. C. Jnana Kausalya, and all other faculties for organizing this event successfully. A special mention of thanks to our student chair, IEEE RAA Society, Ms. Mira Ganesh, and student vice chair, Mr. Shubhas R, third year ECE, and all other IEEE students for aiding in conduction of this webinar. Finally, I thank all the students, faculties, research scholars from India and other countries for their participation in this program. Thank you all. Thank you, sir. Once again.
Thank you, ma'am. Thank you. Sir, I would like to thank you, John, for in your busy schedule, taking a time and coming here and giving us a nice, wonderful webinar over here. And I would also thank IEEE coordinators, student coordinators, staff coordinators, and all the participants, active participants who were till the end of the session. Thank you, sir. Thank you.
Thank you. Good luck with the rest of your SAVANT program. Okay, and thanks again for the opportunity to participate.
Yes, sir.
Yes,
Thank
sir.
you, sir.
Thank you,
sir.
Mr. John. Thank you.
Sir.
Thank you.
And over to the participants, our next webinar is tomorrow at 2:30 p.m. Speaker Professor Fabio Banzaro, topic of reproducibility and benchmarking in AI and robotics. So far, who haven't registered for the session, kindly go through the same link and register. Thank you all. Thank you, participants. Thank you, ma'am. Thank you.
Thank you, Subhash.
Thank you, ma'am.